I also have a set of papers and work in progress on economic determinants of family structure, but I don't. Given how slowly they've progressed, I usually don't brag about those when I. but given that this is PRC, I actually do have papers that are population. Just only have managed to get one published so far. So, all right. So this paper is called Pay for Percentile, and I'm going to present this paper a little bit differently than I normally do, because the beauty of this paper, from my standpoint, is that we have all of these test-based accountability programs, test-based performance pay systems, etc. now that are a big focus in public policy. And if you look at how economists have entered the research and policy debate surrounding these things, for the most part, it has been of the form, we can do the econometrics differently, or we can do the statistics differently or better than people trained in other disciplines. And so it becomes, often it becomes this, this debate back and forth between people who think about the world in treatment and control or fixed effects models versus people who were trained in stats departments or ed schools and they want to talk about Bayesian shrinkage of this or that. And it's all about measurement. And I think the thing that economists have that people from other disciplines don't have to contribute to this area is we actually have a subset of economics called mechanism design that asks the question, if you want to induce people to do certain things with an incentive system, how do you design the mechanism to do that? Okay? And I thought that it was, kind of ridiculous that all the economists that have entered the research on education policy in this area have not actually said, well, let's approach it as a mechanism design problem and talk about how we would design a mechanism to accomplish certain objectives. And for many reasons, I made the decision that, well, okay, I'll try it. It's not that I actually do mechanism design research all the time, but I decided that I would try it. And the next day, my friend Roger Myerson won the Nobel Prize for basically starting the field of mechanism design in economics. So I viewed that as a providential blessing of my decision. And 2 years later, I have a paper. Who knows how long it would have taken without that blessing, but it took 2 years even with that encouragement. So as we go along, I'm going to try to explain the economics in less technical terms, to explain the key ideas about why this thing works in a way that you'll understand if you never had a course in contract theory or you never had a course in labor economics. Because I believe that's the important thing in an interdisciplinary audience, to understand that this is a completely different way of thinking about accountability systems or performance pay systems than people ever think about in educational statistics. And at the end of the day, if you understand how to think in this different box, then I win. Okay? So I don't have to tell the people in the room that are interested in education that this is a big deal now. I don't have to tell the people in the room that one of the things that, regardless of what discipline you're from, that everyone has learned and there's agreement on, is that if you have some set of assessments and people in this high-stakes system know that these are the assessments that are going to be used, you get improvement in the scores on those assessments that, in the words of educational statisticians, doesn't always generalize to other assessments that cover the same domain or the same curriculum. And my favorite example of this is from a paper in the JHR in 2002 by Dan Koretz. And Heckman and Hanashek and I edited this special volume in the JHR. This was a school district in Kentucky that had a reward pay or a merit pay system for their teachers. And they were very proud that this few years after they put in this system, that their third graders were kind of in the middle of the fall of fourth grade in terms of their math level. But then they changed testing companies. So they ordered a test that was supposed to cover the exact same curriculum, but they ordered it from a different company. And lo and behold, they weren't as special anymore when they wrote the contract with the new testing company. But over time, they became special again to the same degree that they had been special before. And then Koretz, being the subversive he is, he got permission to give the exact test that had been given in '86 to a subsample of the students in 1990, and lo and behold, special was now in the eye of the test developer. And so, this is a very stark contrast. The results don't always turn out this starkly, but it's clear there's a lot of evidence out there that when you put in these high-stakes programs, you get gains that are specific to a type of assessment. Now, that can happen for many reasons, okay? But one of the reasons that we want to stress is that if you think about the way that tests are equated, okay, you can think about a series of assessments that have overlap, and then you use the common items in an IRT model to put the two on the same scale. Or you can think about these alternate form methods where you've got, 3 forms or 2 forms, and you hand them out, randomly to kids in a population at a point in time, and then use the fact that you're supposed to have the same population of achievement to equate the 3 forms, okay? But both of those methods have the property that after you've tested one time, one of the strategies for preparing your kids for the second round of testing is to get copies of the first set of forms and drill them on the questions on those forms. Because if it's overlap, you know that a certain percentage of the questions are going to be repeated. If it's alternate forms, you know your kid's going, if it's 3, you know your kid's going to get one of those forms the next time. Okay? And there's evidence in Koretz, and this is for Kentucky. There's evidence in Kenya, and then there's the stuff in Chicago that, Brian Jacob, looked at implicit evidence, but there's also ethnographic evidence that, in the 90s, people were trying to get copies of the ITBS and drill them on questions that they thought were going to be on the ITBS. And so one of the things that we want to do is we want to say, how would you design a system such that people couldn't coach in this way? They couldn't say, we know there's this set of questions, we know some of these are going to be repeated, we'll just have everybody memorize the answer to all of them. Okay? Now, that's not the only distortion created by high-stakes testing systems. I do believe it's an important distortion that's been documented. We'd like to get away from that. And one of the points that we want to make is you can't get away from it in the context of the current systems that educational statisticians and psychometricians propose. And the reason you can't get away from it is that those systems are simultaneously trying to measure achievement growth and provide incentives. In other words, the way that they're conceived, if you look at the VAM literature, the way that those guys think about the world is, we want to measure the contribution of this teacher to achievement growth, and then we want to pay for it. Okay? And so the two tasks of measuring growth and paying for performance are tied up in one activity. Okay? And as long as you tie them up in one activity, then the way psychometricians equate assessments, there's always going to be an opportunity to coach. And there's always going to be a temptation, you know, at a kind of state level or a district level, there was always going to be a temptation to try to monkey around with the scales. Okay? And so we want to get to systems where you can give a brand new assessment every time, so that the exact format, the exact items are completely, you know, unknown, and there's no scaling. We're only going to use the ordinal information in the assessment. Well, now, obviously, if we're only going to use the ordinal information in the assessment, we can't give you any measures of achievement growth. And that's the point of the paper. If you don't try to do two things at once, you can do both things better. And so we're going to propose a world where you give incentives based on the ordinal information of a sequence of assessments that are new every time. And then you can have a NAEP-like system that you use to measure achievement growth. And it has no stakes. You know, it's on an IRT scale like, you know, you want if you're measuring growth. And because the two systems are completely separate and there's no stakes on your measurement system, you're going to get better measurements because people won't have incentives to game the system that you're using as a measurement device. All right? That's where we're going. It always helps to hit the button before you say everything on the slide. Okay? And also the next slide. All right. And and this slide too. All right. And then this is the last thing I said. Okay? Sociology, you know, economists talk about Holmstrom and Mildrum's multitasking model. And sociologists often talk about Campbell's law. Okay? Campbell's law, if you read the original paper from the 70s, there's no theory at all. This guy's an empirical sociologist. This guy does case studies. And he's done 1 million case studies of different government agencies. And he comes to this, what he calls an empirical law. That whenever you have some performance indicator in government and you attach stakes to it, it gets corrupted. Okay? Economists think of that in terms of Holmstrom and Milgram's multitasking model, that if you have a performance measure and there's some action you can take that will move the performance measure without moving real value, people will do that, even though you don't want them to. Okay? What we're saying is, whether you understand Campbell's law as an empirical phenomenon or where you understand it in terms of that multitasking framework, the best way to have performance measures that aren't corrupted is to have your performance system separate from your incentive system. And that's what we're proposing. Okay, so here's how our system works. Pay for percentile. Group students into comparison sets. Okay? And you know, this is the first step is where all the rubber hits the road if you actually want to implement this. But what you want to do is you want to get students into groups such that for any given level of teacher effort that they might have, the conditional distribution of expected outcomes for them on the test at the end of the year is the same. Okay? So you want to get students that are starting at the same place. Okay? Now, exactly how you define students that are starting at the same place is going to hinge on what you assume about the educational production function. And there's going to be different rules for forming comparison sets depending on what you say that function is. Okay? Do I condition on my peers? Do I condition on the resources in the classroom? Do I condition on, different things? It's all going to boil down to what you assume about the production function. Okay? In the simple production function that we start with, all you're going to have to do is condition on the past history of achievement scores. That you've got a long enough history of past results that you can say, these kids are really comparable. Okay? Then within the comparison sets, at the end of the year, you have an assessment that covers the curriculum you're interested in, and you give kids a percentile score in their comparison set. Okay? Now, it's important to realize we're not saying that percentiles are a desirable scale. Okay? Psychometricians always want to think about scale. There's nothing magic about percentiles as a scale. The key thing here is that if I get a 75% in my comparison set, it means that I beat 75% of the kids that started the year just like me. Okay? So, with respect to me, my teacher had a batting average of 75%. When compared to the kids elsewhere in the state or the district that were like me, my teacher won 75% of the time. That's the key. If you sum these percentiles across the class and then divide by the class size, what you have is a winning percentage or a batting average for the teacher. Right? So if Johnny wins 50% of the time and Susie wins 75% of the time, etc., then we can, aggregate across the kids in the class and say this teacher wins this percent of the time. Okay? And the idea is to pay teachers bonuses based on the fraction of times they win. Okay? Now, this is very conceptually different than VAM. Okay? The VAM advocates will tell you that they can take this big regression model and through a lot of magic, they can give you a ranking of the best teacher to the worst teacher in the whole state of Illinois. So we got all the teachers teaching 5th grade math. They're going to tell you who performed the best and who performed the worst in the whole state. And then they're going to tell you which ones are statistically different than the median and which ones are statistically worse than the median. And it's a one dimension of teacher quality. And then they might come up with some system that says, if you're above some rank, you get a bonus. That is not the thought experiment here. Okay? We aren't using any scaling. We aren't using any extrapolation from a statistical model to put people on a one-dimensional performance scale. What we're saying is you get paid for beating the other teachers. And you get paid for beating the other teachers that teach the kids like the kids you have in your class. Okay? And so if some VAM advocate comes along to me and he says, your system gave a huge bonus to some teacher in a disadvantaged school on the west side, but my VAM model says that teacher wasn't really as good as some teacher at Lincoln Prep that you're not giving a big bonus to. It's just that this teacher didn't have as good a competition. And what I'm going to respond is two things. One, you have no idea whether or not one teacher's better than the other in some meaningful sense, because they had very little overlap in their classrooms. And if they're not teaching the same students and you're giving me a performance ranking, Your functional form assumptions, your scale assumptions, and all your extrapolations are making up a ranking when there's no data that's actually, overlapping performance. If we don't teach the same kids, we're not doing the same job, and if somebody says one of us did a better job, they're making stuff up anyway. But the second thing from a policy standpoint is that if that teacher in Lincoln Prep is convinced that she could have taught in this West Side school and really won all the tournaments, well, here's the door. Come prove it. The relevant thing for incentives in terms of paying you to do your job is, are you doing a better job than the people who are willing to do your job? Right? If somebody's teaching remedial math in a disadvantaged community, the performance of people who teach honors classes in Wilmette and aren't willing to teach in that remedial class is irrelevant for how you provide incentives for the person willing to teach the remedial class. Okay? That's the difference in thinking that underlies this system. Okay? Okay. For those of you who know economics, it turns out this is just a generalization of a paper by Eddie Lazier and Sherwin Rosen, who were both here in economics in the 70s. And what they pointed out was that if you had two workers that were doing the same job, say in a law firm, you couldn't measure in dollars the contribution of their work to the firm, but you could rank them, who was doing a better job. That being able to rank them was enough to get them to provide efficient effort. And the reason being able to rank them was enough to get them to provide efficient effort is, imagine they're both providing the right level of effort. Okay? Well, at that right level of effort, if somebody and so then they both have a half chance of winning. Well, if somebody deviates from that optimal level of effort and the other one stays where they are, you've got to try again. You've got a change in the probability of winning that's associated with that small deviation times a prize if you win the contest. And for this infinitesimal change, if that change in the probability times the prize equals the change in the cost, okay, then you're going to be just indifferent between providing a little more effort and staying where you are. Okay? And so that means if we get the right curvature conditions and we have a fair contest, okay, so that the cost of providing effort and the benefits of providing effort are the same for both workers. They're in a fair fight, okay? Their chance of winning, given what the other person's doing, is the same function of effort. Then we can have this condition hold at the efficient effort level for both people at the same time. And so one prize can get them both to provide the efficient effort. Okay? And there's noise in the process. People, their true output has to do with not only what they choose, but also luck, things that happen. And at the end, they both worked equally hard. They both performed equally well, but one got lucky, one didn't. You hand out the prize based on who got lucky. Okay? But the point is, it's not a process that says ex post we want to figure out exactly who was better. It's a process where you say we want to get people in a situation where they have the same chance to win and hand out prizes that ex post are handed out based on luck, but that because the contests are all fair fights and they're prizes, that structure gets people to work. Right? Because everybody knows they have a chance to win. And it's that structure that elicits effort. Okay? What we show is we're going to create a huge simultaneous contest. So that if you think about it, say in the state of Illinois for 5th grade math, and think about it as teams of teachers teaching 5th grade math in elementary school, each team is playing against every other team in the state that has a kid that's like one of their kids. Okay? And we're picking a vector of efforts, not just one dimension of effort, because we're going to pick how much to do classroom instruction and how much to tutor every kid. So we're making a multidimensional choice, and those choices simultaneously affect the outcome of many contests. Okay? And it's going to turn out to be the case that instead of just paying a prize for the winner in a 2-person contest where you pick one dimension of effort, you're going to take your winning percentage over all the contests and multiply it by the same prize. And that's going to give you incentives that instead of giving you efficient effort on one task in one contest against one person, gives you efficient effort tutoring all the kids in classroom instruction in a contest setting where you're playing thousands of contests at once. Okay? And so that was the $20 bill that was laying on the sidewalk for 30 years, that people didn't realize that this same logic that worked when you had one contest, one level of effort, one contestant, it works in this play everybody at once setting where instead of win or lose, you have a winning percentage. Okay? So, in students, okay, to make the math simple, every class has the same number of students. AIJ is the initial skill level of the I student in the Jth class. So the way you want to think about it here to make the math simple is every class is a replica of every other class. So all classes have the same composition. Okay? Now, if there were a bunch of different class types, that wouldn't matter because you would only compete against the classes that were like yours. You know, the way we've structured this. But to make it simple, think about the I equals 1 to n as being places on a baseline achievement distribution. Okay? And so if we're in this league together, I'm playing n contests against you. Okay? We have n students and they all started at the same place and now we're going to have a contest. Now, what a student has in terms of true achievement at the end of the year is going to be a function of this learning by doing function. There's a certain amount of growth that's going to occur that's just a function of where they started, whatever you do. And then what the teacher does in terms of classroom instruction. And then what the teacher does in terms of tutoring the kid at that level. And then a shock that is specific to the match between the teacher and the student. And that's, did you have a good year in school? Were you getting along with your parents? Were you getting along with your friends? So this is the human capital that's produced from matching that teacher and that student. This is the utility function of the teacher. The teacher cares about her expected income. That's what XJ is. And the effort cost of providing the tutoring and the classroom instruction. And the key thing about the effort here, this is a vector of all the tutoring efforts. The key thing here is that you don't care who you spend time with. So if I spend 3 hours with Susie and 5 hours with Johnny, that's the same to me as 5 hours with Susie and 3 hours with Johnny. Okay? That's going to make the math easy. It's actually not essential, but it's going to make the math easy. So if we lived in a world where there was an omniscient social planner that could send instructions to each teacher and tell them what to do, and they had to follow the instructions, then what would the instructions be? Well, the instructions would be to choose the effort vector and the classroom instruction level that would maximize the human capital that you created at the end of the year, minus the effort cost to teachers, minus their outside option, what they could have produced if they weren't teachers. All right? And so, and R here is the price we want to put on this A, this true human capital index that we don't see. And what it turns out is that because every kid has the same return to effort, okay, and because classroom instruction has the same value in all classrooms in this simple specification, then for every I, this is going to be the first order condition. It's going to say pick tutoring effort until the marginal cost of tutoring effort is R alpha, and pick classroom instruction until the marginal cost is Rn, because you get this return for every kid. You get the return of 1 for every kid when you do classroom instruction. And so this is going to say all class, because there's nothing on this side that has to do with J or I, all classrooms are going to have the same level of classroom instruction that satisfies this condition, and all kids are going to get the same level of tutoring. So the other thing, this is not only nice math, we start in a nice egalitarian world where what the social planner would tell teachers to do is treat everybody the same. Okay? And treat everybody the same in a way that maximizes net welfare creation. Okay? Now, the key thing here is that we don't have an omniscient social planner. Nobody sees A. Okay, and the omniscient social planner can't send these instructions that will be obeyed. In fact, what we see here, we see test scores. And what we know is that these test scores are strictly monotonic mappings. So if you have a test score that's higher than another student, you have a level of A. Try cancel, that worked longer before. If you have a test score that's higher than another student, then you really have more skill than the other student. Now you might say, well, that's not true. Tests have measurement error. Okay? It's going to turn out that as long as we can use the whole history of your assessments from kindergarten forward to get you in the right sets, to get you in the right comparison sets, and that you're really closely matched to begin with, it won't matter if we have some measurement error on the final test. Okay? That's just reinterpreting our error term. Okay? So as long as you can get the comparison sets right to begin with, the fact that there's a little measurement error in the test that you're going to hand out the prizes on doesn't matter. Okay? But it's going to make the math easier not to carry around one error term for luck and one error term for measurement error. To just think about the measurement error as part of the luck. Okay? So, and see, now this thing doesn't work. All right, so what we're going to have to do now, oops. Okay. I'm glad this is about the 8th time I've given this talk, or I'd be real nervous right now. Okay. So suppose we lived in a fairyland where we actually knew the scale and we knew the G of A. Okay? Well, then education policy would be really easy because we could take the test scores and turn them into money, and we could just pay piece rates, right? The V is the true value added of the teacher, right? Or the true expected value added of the teacher. R is the price we put on value added in those units of human capital, and we just pay piece rates the same way, you know, you pay agriculture workers for the number of tomatoes they pick. Okay? And if you didn't know the G of A, okay, well, we got the comparison set so that people are matched on their initial A. We just take the average at the end of the year in those sets, and we take that out. Okay? And we're still in business, except now we're just paying R times this. Okay? And this is actually, if you think about it, this is what VAM people are trying to do. Okay? Except they're glossing over the fact that they don't know M of A and they don't know R. Okay? But they're trying to calculate this minus this, except instead of this being a mean within a comparison set, it's a predicted value based on their statistical model. Okay? And so this is what the VAM people think they're doing. Except they're doing a very parametric approximation to this. Okay? The problem with trying to take this approach is that it's scale dependent. And because it's scale dependent, you're going to have knowledge of what's coming before you get the test. Right? If they did alternate forms to do this, the second year we run it, everybody knows one of the three forms is coming. If they're doing overlap, everybody knows, 20-30% of the items are going to be repeated. Okay? And so a scale-dependent system is going to give this predictability. The other thing is the scale itself is an opportunity for corruption. And if you don't believe that scales can be corrupted, then I would draw your attention to what I call scales and political pressure Chicago style. So everyone knows that the way No Child Left Behind is implemented, that there are targets for proficiency that get more stringent over time. Everybody knows it's a huge political problem in states like Illinois, where you've got a large city that has academically and economically disadvantaged populations that are going to have a real hard time reaching a proficiency standard that's set appropriately for the rest of the state. Okay? And so in 2005, 2006, when they went from testing 3rd, 5th, 8th grade to testing all grades, as they had to do on the, rather than just adding to the testing program they already had, adding, 4th and 6th, etc. grade assessments, so we'll have a new set of assessments. They'll be vertically scaled, and we'll equate to the old assessments. Okay? Now, if you look at 3rd grade reading and 3rd grade math, and if you look at 5th grade reading and 5th grade math, and if you look at 8th grade reading, you will see that when they equated, most of, or 40 to 50% in those cases, roughly, of the gains in proficiency that have occurred over the whole NCLB period were in that 1 year. So that makes you a little suspicious about the equating study. But when you get to 8th grade math, we really parted the Red Sea here. We went from 54% proficient in 1 year to 78 proficient in the next year. And, the report that I pull this out of says, well, maybe we didn't get the equating exactly right, but we did the best we could. Now, the fact that the Chicago public schools were under incredible pressure based on this proficiency rate system under No Child Left Behind is not orthogonal to the fact that this is the way the equating study came out. Okay? And the point is, there is no natural scale for knowledge. And so therefore, if you have systems that are scale dependent, you're going to invite this kind of funny business. All right? So if we get to ordinal systems that are scale invariant, it can help us on the coaching because we don't have to have common items. It can get rid of a scale, and that's one less thing that can be futzed around with. All right? So we want relative performance. Only want to compete against the people that teach kids like yours. We want scale invariance, and we would like a system that, at least under some conditions, gets you efficient effort. Okay? How to proceed. Okay, I'm going to explain the two-teacher contest to you. If you understand the two-teacher contest, everything else is just longer equations. Okay? So, imagine that there's only one other teacher in the state that has a class like you do. Okay? And so, you're J and the other teacher is J prime. And we're going to pay you a prize, x1 minus x0, every time your student beats J prime student that they're matched with. Okay? And this is the luck that your competitor had. This is your luck. So this is the error term for student I that determines who wins. Right? It's the difference in your luck and your competitor's luck that's going to determine who wins. And so H is the distribution of that luck term. And so your maximization problem is to choose how much you're going to tutor each kid, how much classroom instruction you're going to give. You're going to have base pay, which is x0, and then you're going to get a bonus every time you beat the other teacher. Now, what's the probability that you beat the other teacher? It's the probability that that luck term is less than the difference between the tutoring that you gave that student plus the difference in the classroom instruction you gave that student. Okay? Minus your cost of effort, minus your outside option. Now note, when I solve this problem as teacher J, I take what J prime does as given. Okay, so this is a game. I pick EJ and TJ. My opponent picks EJ prime and TJ prime, and then we see who wins the end contest. Okay? An equilibrium to this game is where, given what I chose, you're happy with what you chose, and given what you chose, I'm happy with what I chose. Okay? Well, if I take what you're doing as given, my first order condition, so now I'm just going to take what you're doing as parameters, and I'm going to say, I'm going to maximize against that. Okay? Well, that would mean that I would pick levels of effort that satisfied these first order conditions. This is just taking derivatives. There's n of these, so we got n plus 1 derivatives of that function, holding constant the tj prime and the eij primes. Okay? Now, my opponent's going to have the same first order conditions, except these things are going to be reversed. Right? Everywhere where I have a J, they're going to have a J prime, and everywhere, okay? So if we guess that we have an equilibrium where we both choose the same thing, this is a 0 and this is a 0, and this becomes H0. Okay? And then if we say, what if we pick the prize to be R divided by H0? And we plug that in to that. Those would be the first order conditions for both of us. Who remembers where those came from? Those are the first order conditions for the omniscient social planner. If the omniscient social planner told everybody to do the efficient thing would satisfy those conditions. If we play this game against each other, there's an equilibrium where we both pick the efficient thing to do. All right? Now, the question for policy heads is, could you ever get the prize right? Okay? Well, you know, in this production function, R is really the value of 1 hour of classroom instruction or 1 unit of classroom instruction, right? Because the coefficient on T is 1. So we've normalized it. So R is what society gets from having a unit of classroom instruction. You might think, and there are certain assumptions about elasticities of supplies to different occupations, that a good approximation of R is just going to be the price of college-educated labor at the skill level that you want in your school district. So we can look that up on the BLS website. Okay, this is in the two-teacher contest, this is a proposition that formally states that there is an equilibrium. This is the one that says when you only got 2 teachers, it's unique. It's the only equilibrium of the game. Okay? This is the slide I thought I was talking about. See, it's worse when I run ahead and I run too far ahead. But this is the one I thought I was talking about. What you want to think of H0 is, H0 is this derivative we were talking about before. If I give just a little more effort, what's the probability that I win? Right? If I give just a little more T, I'm going to move my kid's A by just a little bit, and it's the height of that density that's going to determine the change in the probability I win. So you can imagine doing a set of experiments where you gave a small amount of tutoring sessions or a small amount of classroom instruction sections to a random sample of kids. And then you looked at the average deviation on their winning probability from 1/2. Okay? And that change of P divided by change in T, the time that you gave them, is going to be approximately H0 as long as the T is small relative to, what you think the importance of the shocks are. Okay, so if you thought that the random things that happen to kids in terms of being equivalent to withdrawing or adding effective instruction, if you thought that the standard deviation on that was maybe a month of effective instruction, that the things beyond the teacher's control had a standard deviation of either giving them an extra month of good instruction or taking away a month, then if we give them, 2-day prep periods, that's going to be trivial relative to the variance of that shock, and these experiments are going to tell us something about H0. The other thing is you can make a parametric assumption about what those shocks are, and that parametric assumption will tell you what H0 is, and then you can calculate the prize. And so let me tell you how this worked. John List is running experiments in Chicago Heights, and I don't know whether he's going to do it or not. But he just wanted to know, if I ran pay for percentile in Chicago Heights, what would the bonus schedule look like? Okay? And what the bonus schedule would look like is you would take your overall winning percentage, okay? And you'd multiply it times $5,000 based on some assumptions I made about what H0 is. So assumptions that I thought were reasonable. Okay? So, you know, plus or minus $2,000 or $3,000, this implies a bonus system where the maximum bonus you could get if your kids beat everybody they were competing against would be, you know, $5,000 to $7,000 on a base salary of, you know, 30 or 35, and the worst you could do is get 0. And most people would be concentrated halfway in between. Okay, so that, in practical terms, that's the range of bonus pay that we're talking about here, if you kind of back of the envelope figure out what this model means. I'm not saying anyone should go run this and use those numbers. What I'm saying is, if they came out to be that the bonuses should be a maximum of $50,000 and be centered on 25, then you'd worry about the model, because that would be crazy for people that worked on a base of 30. Okay, but it gives reasonable numbers in terms of what it implies, given the wage structure for college graduates, and, you know, when you actually do it. This formula tells you how you set the base pay, and you basically have to set the base pay high enough so that you cover the outside option. U0 is what you could make doing something other than teaching.
What assumptions do you make about luck here? Is it that it varies randomly, or that it's different from year to year?
It's different from year to year, and but the key assumption is I can't see the luck during the year. That if things are going on and Johnny's relative to kids that are like Johnny in every way, Johnny's really going to do terribly this year, I can't figure that out by October, or this won't work, right? The shock has to be beyond the control and knowledge of the teacher. Now, when you think about, you know, how I said you'd implement this, you'd condition on the whole history and the demographics and everything. That's not, you know, an unbelievable assumption, because, you know, forecasting how they're doing relative to kids exactly like them is a tough thing to do. Okay? But the real key assumption here is that I can't figure out early in the year who's got a big epsilon and who's got a small epsilon, or then I don't completely give up, but I cut back on some kids, you know, who I think are going to win anyway, or who have no chance.
So you're saying you're conditioning on the history and demographic composition of the classroom, right? That's
Not yet.
Not yet, but not yet. That's where you are.
By the end.
So is it possible for some teachers to have persistently bad luck then? So
It wouldn't be luck.
I guess as you define it, yeah. But that luck accounts for a lot of things that people think is associated with performance, right? You talked about, like, you know how you're.
It's fine. You got to get your head straight here, okay? Everybody that has written on this prior, they want to think about it as, first we measure performance, then we isolate the part of performance that had to do with the teacher's behavior, and then we reward that. We're not doing that here. What we're doing is we're saying we want to have contests, and the only thing we require is that you have to have a fair fight. And if we can construct these fair fights, then we can pick prizes that will make everybody work hard. That's the, and at the end of the day, everybody will have worked hard and we will have handed out prizes, but we won't have any measure of achievement growth. Okay? But we will have gotten people to work hard without the coaching, without the scale manipulation, without a lot of the funny business. And then let somebody else run a NAEP-like system to tell us whether achievement's growing in the district or not.
I'm still not clear. How do you operationalize the fair fights? I mean, you've said you split them up into groups, which means 0 weight on people outside. But then you said you you'd actually run regressions. I mean,
Well, there's
you put everybody in one big group.
it's going to be very context specific, and a lot of it's going to depend on how much data you have. If you're doing this in California, this is the way you're going to do it. You're going to say, I can non-parametrically estimate this. What's the conditional distribution in the state of end of the year, this should be S to do the consistent notation, of the end of the year test score, given where this kid started, and A star is where all his classmates started, and this is all the characteristics of the classroom, like do you have an aide in the classroom, do you have computers, is this a poor neighborhood, whatever. And if we're in California, then I can non-parametrically estimate this distribution, and every kid has those characteristics. I can put his score in F hat, and I can give that kid a percentile. Okay? When I was talking to them about how to do it in Chicago Heights, where they only have a few thousand kids, we were having to do some cheating. Okay, in terms of making some assumptions about smoothing over some stuff. And we, actually did it in a much less sophisticated way than this. Okay, so there's no one answer to that question. All right? Now, what is all of this stuff? Well, this is all the math if now you're going to play K teachers. Right? Instead of just playing against one other teacher, I'm going to play in a league where there's K plus 1 teachers and we're all going to play each other. Okay? More complicated math. Take the original prize. Now we're going to get fancy. Take the original prize, R over H0, divide the prize by K. So when I was playing one person, it was R over H0. Now I'm going to play K people, and so what I win per contest is going to be 1/k. The first order conditions for the players collapse again to the planner's first order conditions. Okay? So the same prize scaled by the number of contestants works. Now, imagine that we let K get very large. Okay, so you're playing against hundreds, this is the California thing again. You're playing against hundreds of other classrooms like yours. We can think of this as a random variable that says, let's draw from the distribution of all kids in the state that started at level AI. Okay? And the probability that that random variable is less than your kid's score is your kid's percentile in his population comparison set. Okay? And if you take the maximization problem that we had with an explicit K, and you let K go to infinity, then you end up with this that says you take the Lazier-Rosen prize and you multiply it times the sum of the percentiles. Okay?
Have you tried thinking about this beyond one contest? I'm just kind of wondering when you add time into the equation. So for instance, next year's contest is going to be dependent on last year's contest. You're just going to affect the historical scores of the child over time. Like if you follow the kid through like first grade, second grade, third grade, etc.
That's one of the reasons that you want to make sure you implement this at the school grade level. If you just did it at the school level, then there would be an incentive for the 5th grade teachers to try to sabotage the 4th grade teachers to get their kids in the wrong league. Okay? So you want to do this at a grade team level. All right? Okay. So now, We did this with a very special production technology. Let's consider a more general technology that says that how much I learned during the year is a function of all my peers' ability level, is a function of how much the teacher teaches us, and also a function of how much everybody gets tutored. And so this is instructional spillovers. This is peer effects. And all we need here is that the cost function stays convex and that this is concave. Okay? And now, the planner's problem looks different. Instead of having that one term here, what we have is this is the benefit of me and all my classmates from tutoring me a little bit more. And this is the benefit of me and all my classmates when the teacher teaches a little bit more. Okay? And it turns out that when you write down this is the K-teacher contest with the same prize and this technology, you once again get an equilibrium that matches the planner's problem first order conditions. Distributions of A and and students learn at different rates, or you have different compositions of A and their different peer effects. The solutions to these equations, in other words, what's the optimal level of effort to provide, is going to vary with what type of class it is. Okay? And so you have the same bonus structure for every classroom, but in classrooms where that bonus structure is going to induce more effort because it's socially efficient to work harder in this class, okay, you're going to have to pay higher base pay to get people to work. All right? Now, that's the first thing to notice. The second thing to notice is before, when we said you compete holding constant your peers, that was just to keep the same story all through the talk. With that separable technology, you didn't have to. You could compete against every kid in the state that was like your kid, whether he matched at the classroom level or not. Now, it is imperative that we condition on the classroom composition, because the classroom composition determines the value of effort to any one kid. When you got these spillovers and these peer effects, and you want to have a fair fight with respect to Johnny and Bob, if Johnny and Bob don't have the same peers, then it's not a fair fight. Okay? And so that's why in the most general case, you want really large samples so that you can, trust that you're getting percentiles that represent, actually the right comparison sets. Okay.
Can the allocation of effort change within the classroom because of the peer effect, or we still?
In this technology, it doesn't have to be the case anymore that all kids get the same attention. But the differentiation among the kids is socially efficient.
Right, and should be
Right.
the mirror.
Okay, so think about it in terms of the heterogeneity to make it simple. If all the other kids learn at the same rate, but one type learns twice as fast, okay, you'll put more effort on those kids naturally in this structure, because when we start competing, think of it, well, I pick this and then you get to pick and then I get to pick again. Instead of a static Nash, just think about where you say what you're going to do and I get to respond and you get to change, and we do that till we don't want to change. Well, if the kid's learning twice as fast for every hour I put in, that process of I do this, you do that's going to stop at a higher effort level naturally for the same prize. And it turns out it's going to stop at exactly the right point if we hold the prize constant. So what this does here is the prize is set in a way such that if it's more efficient to give certain kids more attention because they're getting more out of the attention that you give them, because it's a contest, the prize induces you to do that naturally. Okay? All right. And once again, I've said everything already. Here's the, except this, and this is important, okay? I hope that there's been some time in the last hour when you've said to yourself, this seems like a magic trick. That, you know, how in the world do you pick this prize and get all these good things to happen? I hope someone has had that response, because when we discovered this stuff, I certainly had this, you know, how in the world did it turn out this well? The key thing that we're assuming here that looks innocuous but is really a strong assumption is that H0, that this V, this noise distribution, is the same for all the contests. So whether you're the smart kid or the dumb kid or the medium kid, you've got the same error distribution you're drawing from. If you didn't, then you'd have to have a different prize for every type of kid. Okay? And it would be impossible to run those experiments and pin down exactly what the prize should be for each different type of kid, because if we had two types when we ran those experiments and we found a bigger change in the probability for one type than the other, we wouldn't know whether it's because those kids learned faster or because the shape of the error distribution was different. Right? And there would be a million different combinations of differential rates of learning and different shapes of the error distribution that could reconcile the difference in the outcomes from the experiments for type A and type B. Okay? So the real, you know, detail that you want to be aware of that makes this not magic is that if you wanted to be confident that one prize for all types of kids was the right thing to do, you'd have to have information that you really are going to have a hard time getting. Okay? And if you thought those chance distributions were different at different points in the achievement distribution, then you shouldn't have a common prize. Okay? But it sure did make the math easy. All right. So let's think about this in the 5 minutes I have left in terms of what people do. With the exception of the TAP program, most of the existing systems have the form. You sit down with your principal and you negotiate targets for each student, or you sit down with your principal and file some paperwork based on last year and make a case that you were exceptional. Now, it shouldn't surprise anyone that when bonus pay is based on negotiated targets, either ex post or ex ante, we hand out a lot of bonus pay. Okay? And so the TAP system and our system are the only systems out there that I know a lot about where not everybody can be exceptional. Okay? It's a zero-sum game. Somebody has to be the best and somebody has to be the worst. All right? I want to argue that's an important thing for a performance pay system to have. Otherwise, the performance pay system can just become political cover for increasing base pay for everybody. Okay? And that's what I call lesson number 1, draining Lake Wobegon. All right? If everybody's competing for a fixed amount of bonus pay, and every dollar that one teacher wins is a dollar another teacher loses, that system can't be gamed in the way that these negotiation systems can be gamed. Second lesson, ordinal is enough. You don't need an IRT scale, you don't need a developmental scale, you don't need an equating study, you don't need proper equating methods, you don't need a vertical scale, you don't need any of that stuff that psychometricians obsess about in order to run an incentive pay system for teachers. You can get the incentives right just based on context and the ordinal information. We would do well to take that approach, to use ordinal information and contests for incentives, and have a completely separate system for measuring how well the school system as a whole or how schools are doing in terms of promoting achievement that had no stakes, because that would give us performance measures that weren't contaminated by the presence of incentives, and we don't need to measure performance in order to provide incentives. And that's the conceptual problem with the existing literature. All the VAM advocates, all the people that work in educational statistics think that it's a two-step process, that first you have to measure performance and then come up with a system to reward the performance measures. Okay? And that those are two steps in one process. And the first step is not necessary. And if you separate the provision of incentives from the measurement of performance, you will do both jobs better.
Presumably you want those two tests that you use to be quite similar. If you think that the measurement is capturing something important, you don't want the...
You want them to cover the same curriculum.
Right.
But, you know, the one that's measuring performance, it can be vertically equated, it can have overlap, it can be from one of these series of assessments. And who cares? There's no incentive to go coaching to that assessment because it's not what you get paid for. Right? And if it's done randomly like NAEP and done anonymously, you know, you would have to set it up so they were convinced that there wasn't going to be any double cross and say, oh, you know, we're going to take back part of the bonus money because you had a bad year on this. But if you could make a credible commitment that there was a wall between the two, then you'd get really clean information out of the low-stakes system because there's no incentive to mess with it, and you can have, you know, all the psychometric properties that you want, enough, you know, overlap to have proper equating. All right? Now, caveats. You don't want teachers in the same school competing against each other. You want them competing as teams against the other teams. Okay? Because, you know, the person who knows best how Ms. Smith can improve is Ms. Jones across the hall. You want them working together. And here's the big part. This is a system where it's contests that are a fair fight. So implicitly, all the teachers have the same talent in this world that we've been living in. You know, the ultimate goal of this research agenda is, you know, if you're going to implement this, you want to control for the experience and the support and all the things the teacher has. But if you really thought differences in teacher ability were important, then you might want to think that there's a new paper down the road that hopefully one day we can write that says you have the following components. You have a tenure clock, the number of years you teach. You have a class size. You have a K, the number of schools in your league. Those things determine the total number of contests you play before you come up for tenure. Then there's a winning percentage. And if you don't cross that winning percentage, you don't get tenure. Well, if you backload compensation such that to, you know, get the big pension or the big bonus or whatever, you have to have that career winning percentage, the teachers who know they're not any good are not going to start. And the ones who learn fast they aren't any good are going to quit. Okay? And so there are ingredients here for building a tenure system around winning percentages that would screen out poor performing teachers in a way that the current system doesn't. And, you know, that's kind of the long-term research agenda here. As you can imagine, once you make this dynamic and you have more than one type of cost function, the math gets uglier. And we haven't figured out how to do that yet. But, you know, having the performance measures be relative performance measures based on ordinal content in terms of performance measures that go into incentive pay, I think is a valuable idea, and I think it has a lot of benefits for education policy. And I'm 3 minutes over, and I appreciate your patience.